Hi everybody, this is Mr. Murphy and I'm going to be taking you through day 4 of chapter 10. We're going to look at a couple of theorems that are really going to help simplify things when trying to find our roots and when we begin graphing. So this is kind of a little bit of an intro into graphing with our higher degree functions. At the start here, we're just going to pick up a little bit where Mr. McGivney left off with dividing. So in your last class, you looked at dividing polynomials. You use both long division and synthetic division. I did the work out for you on these first couple. You'll see in the notes here, this is following worksheet C. So if you took x to the third plus 5x squared minus 20 and divided it by x plus 3, this right here would be our answer if we were to divide that out. So what you're looking at is x squared plus 2x minus 6 minus 2 divided by x plus 3. So what that means, when you see that last term like that still has a denominator, that means that there was a remainder. So it means that you still had this remainder of negative 2 when you divided the original polynomial by the x plus 3. Another way that you could write this, you could multiply the x plus 3 to the other side, and then you'd have your x squared plus 2x minus 6 minus 2 over x plus 3, just to kind of show it written in a little bit of a different form. So the question here, is x plus 3 a factor of the polynomial? So when we're determining whether or not it's a factor, we need to say, does it go in evenly? This obviously doesn't go in evenly, right? So we can say no, and if we're saying why, it's because when we divided it, we had a remainder. So that means that this is not a factor there. Let's take a closer look at this just to kind of figure out where we're going with our remainder theorem. If we actually figure out the value of p of negative 3, so when our x is negative 3, so you might be wondering, where's that negative 3 coming from? It's saying if we took the x plus 3, the value that we're checking the x value at is negative 3, so it coincides with that x plus 3. So if just kind of do a little work below here, we got p of negative 3, we would have what? We'd have negative 3 to the third plus 5 times negative 3 squared minus 20. So if we do all that out, we have negative 27 plus, that'd be 5 times 9, so we got 45 minus 20, right? So we got negative 4, so that's going to end up being negative 2. So what you should notice, p of negative 3 equals negative 2. What was that equal to? That was equal to the remainder that we got. That's our first big theorem of the day. So our remainder theorem, if p of x is a polynomial, then p of b is equal to the remainder when p of x is divided by x minus b. So that's kind of what we just saw with that last problem. All right, let's see how this works and how it's going to help us with our roots. If we have x to the fourth minus 1 and that was divided by x minus 1, we would have x to the third plus x squared plus x plus 1. So you can see that this goes in evenly. So another way of writing this, x to the fourth minus 1, if we wanted to write this in our factored form, we could say x minus 1 times x to the third plus x squared plus x plus 1. So we're just multiplying that across. Is it a factor? I kind of just said this. This would be a yes. The reason is we have no remainder this time, right? Remainder on the first one, so it was not a factor. This has no remainder. So the value of our polynomial on this one, if we got x minus 1, we want to check p of 1. If you plug in a 1 value for this, right, we would have 1 minus 1, which just equals 0. All right, that's our indicator that that is a factor. So our factor theorem is just kind of an extension of our remainder theorem. If x minus b is a factor of p of x, or it would be a factor if and only if p of b equals 0. So this is a really important theorem that's going to help us out quite a bit when we're trying to find our roots and we're trying to write these polynomials in our factored form. All right, so let's just kind of practice a little bit with that. So if p of x equals x to the 1,000th minus 1, if we wanted to use our remainder theorem to figure out what would happen when p of x is divided by x plus 1. So what that means is we want to check at p of, I wrote that wrong, let me erase that real quick. We want to check p of negative 1. So if we plug that in, we have negative 1 to the 1,000th power, which we know is just going to equal 1, minus that 1. And we get that comes out to 0, so that's good. So that means that when we're checking with our factor theorem, is x plus 1 a factor? The answer to that would be yes. Any of our factors are our roots. So is it a root? That would be yes. So this is a huge thing. The question is, how do we know which numbers to check? That's where we need to kind of turn the page here. So how we're going to be able to figure this out is we're going to use what's called our specialized rational root theorem. So today's lesson is going to look at a rational root theorem with our lead coefficient as a value of 1. In next class, you're going to look at what you would do if the coefficient changes there. So if you had a 2x to the third, 4x to the fourth, whatever it may be. So what we're ultimately trying to do with this stuff, with our higher degree functions, we want to start by just factoring our functions. That's kind of going to be our first step. In order to write it in that factored form, we need to figure out at least one of the roots. So we're going to list all of our possible roots, which we're going to look at how to do in a second. We're going to test them. So we're basically going to, that's what part B is doing here, is we basically want to find a root that works. We're going to use synthetic division, so we're going to be incorporating what Mr. McGivney's lesson did with our division. So we're going to use synthetic division to factor this down and rewrite it in our simplified factored form. Once we do that, we should be able to have a pretty good indication of what the graphs might look like. All right, so the key thing here, a specialized rational root theorem. I'm going to start, this is very important, something we're going to be using quite a bit. So for a polynomial p of x with leading coefficient a equals 1, any integer root, so obviously that's important, any integer root will be a factor of the constant, right? So our constant, that's our number at the end there without any variables attached to it. All right, so I'm circling this or boxing it. Obviously, this is extremely important. This is telling us what values to choose. Because on the last page, I was kind of giving you the values. We were looking at them. Obviously, there's an infinite amount of numbers that you could check. So this is letting us know which ones are the ones that are potentially factors. Okay, so first problem here. We got f of x equals x to the third minus 4x squared minus 3x plus 2. What we want to do with this is list all of our possible roots. So I'm going to say PR for possible roots. Using this new rational root theorem, they're factors of our constant here, right? So 1 and 2, those are the only factors of 2. The difference here, it can be plus or minus with these. So plus or minus 1, plus or minus 2. And sorry if you can hear my kids screaming in the background there. I'm sure it's a little annoying, but I can assure you it is more annoying for me. So these are our possible roots. So we want to test these roots to figure out which ones are our actual factors. So if we're testing them, we're checking, all right, what's f of 1? So if we plug 1 into this, I'm just going to I'm plugging this into our original function. We'd have what? We'd have 1 minus 4 minus 3 plus 2 at the end. Right? So we're at negative 6 plus 2. We're at negative 4. So that means that is not a root. Right? If we continue on with this, if we check f of negative 1, this is now going to be negative 1. It's going to be, it's going to be still minus 4. Plus 3 plus 2. So we are at negative 5 plus 5. So we are at 0. That's good. That means we can kind of move forward with this. This is our root that worked. So that means that the actual factor in this case is if x equals negative 1 is the root, so the factor is going to be x plus 1. That's something that we've already seen a little bit in this chapter. Okay, we want to use that factor. If we know that that's one of the factors, if we divide the original by that, we can figure out what the other factors are. So the easiest thing from last class, obviously synthetic division was much simpler than doing our long division. So we put our little recap from yesterday. We put our negative 1 on the outside here. We're putting our coefficients from our function, right? Bring down that first number, and then we're multiplying across. So negative 1 times 1, we're at negative 1. We add those down, so we're at negative 5. Multiply it, add it down, so negative 3 plus 5, we're at 2. We multiply it, negative 2, and we get to 0. So we can box this off. This is this needs to be 0, right? If this isn't 0, it means that there was a remainder, which also means that obviously that wasn't a factor. So if you got up here that this was a factor, that should always coincide and be 0. So if that's not, it means check your work, something went a little bit wrong. All right, what this means, that means that this is x squared minus 5x plus 2. So if we're rewriting this in our factored form, we could say that f of x equals, don't forget the factor that we found originally, so it's x plus 1 times x squared minus 5x plus 2. right? If you could continue factoring that, so the x squared minus 5x plus 2, if you could continue factoring that, you obviously would want to do that. In this particular case, we cannot, right? So if we're saying list all of the roots, we need to figure out, we know that we know right off the bat, we know that one root is going to be the -1. That's the one that we found already. For the other one, this is not factorable. So if we have x squared minus 5x plus 2, and we're trying to figure out the roots, what can we use? We can use our quadratic formula for that. So we can say, all right, x equals, we got 5 plus or minus square root of b squared, so we got 25. It would be what? Minus 8 all over 2, right? So 2 came out weird, so that was over 2. So if we simplify this, we have what? We got 5 plus or minus rad 17 over 2. There's nothing that we can do with that, so we get that we have that being our additional 2 roots with that. Just to recap, the roots, obviously the number of roots match up with the degree of the function, so it should kind of be clear to everybody. We got the 3 separate roots there. We got -1, then we have 5 plus rad 17 over 2, and then we have 5 minus rad 17 over 2. So just a little bit of a recap with this. Whenever we're given an original function, if it does have integer roots, rational roots I should say, we can use this rational root theorem. We can find the possible roots, which are always just a factor of the constant. We test those possible roots by plugging them into our original function to see which one works, meaning which one gives us a 0 for an answer. We use synthetic division to find the remaining roots, and then from there we should be able to graph these. So if we flip to the next page, if we go to graph this, a little tricky just because we got kind of have to look back a little bit, but what we want to label with this, we want to label our intercepts, obviously. So the roots, the reason we're finding the roots, those are our x-intercepts. So we know that we have -1, 0 as one of our roots. And then if I'm just kind of on the side here, if we check 5 plus rad 17 over 2, take a second, put that into our calculators, just so I know kind of approximately where this is, and we could probably do it without the calculators, but it's about 4.56. So it's going to be 4.56 comma 0. If we did 5 minus rad 17 over 2, if I do that out, that comes out to 0.44. So it would be 0.44 comma 0. So those would be our kind of additional 2 roots there. So if we graph these, we had 0.44, and then we had the 4.56, so we'll say that's about right there. How we get an additional point with this? So if we were to look back at just our original function here, so I'm looking at our problem, easiest thing to do is always the y-intercept if we're in our standard form here. So if we make our x value equal to 0, we can see everything goes away except that 2. So we've got 0, 2 as our y-intercept. So couple things. If we've got all these points, if you're saying, well, how do I know how this is going to connect through, right? We should know that this started as what? This started as an x to the third, right? So we should remember that our parent function of our x to the third looks a little bit like that. So that should hopefully give us a little bit of an idea of our general shape. It's positive, so we know that it's going to start low and end high with this particular one. So for just a really rough sketch of this, you can see we're kind of going like that, and then, oh, I went a little too far, sorry, I wasn't looking. And then we're coming down and going back up at that point right there. So obviously without a calculator or without plugging in a whole bunch of different points, you wouldn't know how far down this would go, you know, for a relative min before this dips back up and so on. So you kind of just want to give these a rough sketch at this point. I'm going to go ahead and just label the intercepts that we have really quickly here. This was our 5 minus 17 over 2 comma 0, and then this was our 5 plus 17 over 2 comma 0. So lot of 3 new theorems there. They all kind of coincide with each other. As far as the most important part of today's lesson is definitely just understanding that rational root theorem, identifying the fact of what the possible roots are. Once you have those possible roots, knowing how you can, figure out which of those roots works, and then from there using your synthetic division to kind of rewrite all of this in factored form. So hopefully that made sense. Any questions, please direct to your classroom teachers. As far as the homework goes, there'll probably be an exit slip that's posted for you guys to complete. And then into your next class, Mr. Scott will take you through what to do if you have negative lead coefficients, if you have coefficients greater than lead coefficients greater than 1, and so on. So, all right, thank you very much. Have a good day.